So, what we're going to talk about today, okay, are differential equations. Okay? So, these are, okay guys, zip it, put the newspaper away, pay attention. Okay. These are, differential equations are basically equations where they're written in terms of a derivative instead of a normal y. So basically, these are equations written in terms of a derivative. Okay, so an example, y equals x cubed plus 5. This is a normal equation. Okay, but y prime equals x cubed plus 5. This is a differential equation. Okay. All right. So basically, these are just equations written in terms of the derivative. Okay. Any problems with that? It's fairly straightforward, right? Okay. One thing to remember, too, and this will be kind of a common theme throughout differential equations, the derivative is representative of what? What does the derivative ultimately represent? Not necessarily limit, but yes, limit ultimately, but slope. Okay. When you see the equation of the derivative, you're finding the slope of it, okay? Slope of a function. So keep that in mind because we're going to keep coming back to that notion. Okay? But here are some examples then, okay?
Does that say normal?
Yeah, just normal as in the normal equation. Yeah. Okay? So 2 examples here, okay? All right. When we talk about differential equations, we're going to do several things with them. One, we're going to look at how to find solutions to differential equations. We're also going to look at the different ways you graph differential equations, okay? But let's start off by talking about solutions to differential equations, okay? Okay. Okay. So, the solution to a differential equation, okay, Hayes, pay attention, okay? The solution to a differential equation y prime is any equation y equals f of x whose derivative is y prime. Okay? So, basically, a differential equation is essentially, the solution is, yeah, it's fine. The solution is doing the antiderivative to it, essentially. Okay? That is, I got an equation, a differential equation, so it's a derivative. I'm finding the original equation that gives me that derivative. Now, notice how it says is any equation y equals f of x whose derivative is y prime. Why do you think that could be the case?
There's numerous equations.
There could be lots of different equations, lots of different solutions that give me y prime. Okay?
There'll only be one.
You've got different types of solutions, if you will. In fact, there are 2 types of solutions. Okay? Okay. You have what's called a general solution. And what's known as a singular or specific solution. Okay? Now, the difference between the two is with general solutions, okay, constants are not specified. While with a singular specific solution, constants are specified. Meaning that constants you're actually given the constants. So an example of what I mean by that, I've got one written up here. I'll just write it over here. Okay. Okay. So an example of this. Okay. Now let's say dy by dx is equal to x cubed. Okay. Then y equals x to the fourth over 4 plus c. This is a general solution. Or the general solution, I should say. This is the general okay? Because my constant c is not defined. Any constant out there could be the case. In fact, actually, I should say a general solution. I should go back because I can write other solutions or other versions of this thing where the derivative gives me x cubed, an x cubed alone. But notice how c is not defined here. We're just said there's a c on the end. It's like that plus c we always have at the end of integrals. Well, that means we're finding general solutions, and there will be an infinite number of general solutions. Because c could be anything. C could be 5. It could be pi. It could be minus 456.
Wow.
Okay? Anything you want it to be. Okay? That's a general solution. A specific solution.
Can you scroll up just a tad?
Sure. A specific solution, right here, is any solution where that c is defined. So if I wrote out y is equal to x to the fourth over 4 plus 7, this is a specific solution. Because our constants are defined in that way, okay? I can write another specific solution too. I could write, for example...
How would you get that specific solution?
Various ways. You could be given like conditions in the problem that will let you be able to solve for it. You could be told that some sort of constant on the end is 7. There's lots of different ways. From just x cubed alone, you're not going to be able to figure that out. Okay, you would just know, but it's a possible solution. Okay, one that's specific because again, 7 is given to us. All right. And so we can go through and find other specific solutions as well. They're all, though, come back to the fact that these are both derivatives, or sorry, these, if I took the derivative of both of these, would give me x cubed. Okay? Would give us our original differential equation. Okay? And so that's what we talked about with specific solutions. Any questions about that so far?
Nah.
Okay? Let's look at an example of different types of solution sets that you might get. So an example in which you might do something like this might be something along the lines of y double prime minus y equals 0, okay? And you could be told, test to see which of the following work as solutions to this thing. Our first one is something like the sine of y is equal to sine of x. Our second example that we'll do is y is equal to 4e to the negative x. And our last one we'll do is that constant e to the x, or y is equal to constant e to the x, where the constant is not given. Really?
Yeah, your little thing fell off.
Oh, the little back of the pin? Yeah, that doesn't matter though. That's... Okay, so what we're going to do here is basically we're going to test each of these out and see which one works as a solution to this thing. That is, that makes the equation written up there work. This is a differential equation because it's an equation involving a derivative. In this case, y double prime. Okay, and we're saying, okay, which of these equations has it where if I subtract y from y double prime, I get 0? Let's start with y equals sine of x. Okay. What's the derivative of the sine of x?
Negative cosine. No,
derivative. It's just cosine of x. Okay? And y double prime is what?
Negative sine.
Negative sine. So, if I put that into this equation, well, does it work?
Yeah.
Minus sine of x minus sine of x
No, it doesn't.
equals 0.
No.
So this is not a solution.
I said it doesn't work from the beginning.
All right, guys.
Okay.
Okay. How about this next one right here? Okay. What's y prime going to be?
4e negative 4.
Okay, so negative 4e to the negative x. Remember, it's e to the x, so it's 4e to the negative x. That part repeats, and then you multiply it by the derivative of negative x, which is negative 1. So, negative 4 e to the negative x. So what's the second derivative then?
Positive.
It becomes positive again.
So then it does work.
Does this one work? Absolutely. 4e to the negative x minus 4e to the negative x is equal to 0. So this here, this is a solution.
It's y prime.
Okay? Because it works. It satisfies it. How about the last
No,
one?
that doesn't work.
Yeah, it does. Dog, do you math?
Wouldn't that become positive?
Oh
wait, no,
God.
never mind.
Yeah.
I was thinking y prime.
There you go. All right. Now, how about this last one? Will this one work? Look at it carefully. Okay? What's the derivative of that thing? It's c e to the x, right?
Yeah.
The c doesn't go away. It's a constant out in front. Okay? So my first derivative here is c e to the x. What's my second derivative going to be?
C e to the x.
Also, whatever that constant is, e to the x. So does that make this thing work?
Yes.
Yeah. So this is a general solution. Why is this one a general solution?
Because it has a c.
Because our constants are undefined. Okay? So that's a general solution because the constant is undefined. Well, this one is a specific solution because we don't have any unknown constants in it. Okay?
Okay.
Wait, how does the second one work?
What do you mean?
Isn't it minus negative 4 e to the negative x?
And what's minus negative 4? Which two minuses do?
You would be adding.
It makes
So
it positive, right?
Yeah.
So y double prime is 4. This is positive 4. And y double prime came first, so it works.
Yeah, so 4
It's y
minus
and y.
negative 4
No,
would be 8.
it's y,
The
not
y
y prime.
minus.
Look at the black one
Yeah.
and the blue one, not the red one.
Oh, right.
Yeah, the red one's the intermediate step,
I
okay?
should have color-coded the equation at the top.
Whatever. Alright,
You guys shouldn't have written this in.
That would work.
but
That would have been very cool.
this is but this is an example of how you might use these things, okay? We're going to look at more and more examples of when we do stuff with these differential equations in the future. This is an example of how they work, okay? What we're going to do, kind of tomorrow actually, is we're going to start looking at of how to find solutions if given a differential equation, okay? But right now we're going to move on because we've got other things to talk about with differential equations, okay? What we're going to look at next is graphs of differential equations. I cannot spell that. Differential. Okay. Equations. Okay. All right. There are two types of graphs that we're going to look at here. The first type we're going to look at is what's called solution curves. Okay? Okay? Now, solution curves is when you graph the solution to the differential equation. So we're basically just graphing a regular function. However, you're graphing all the different types of solutions you have. It could be a set. Now, obviously, you can't graph every single solution because, as we've established, there's usually an infinite number of solutions. But you'll be graphing sets of solutions. So you'll have multiple curves on a single graph that you look at. Okay? So solution curves. This is a graph of a set of solutions to the dq, or to the differential equation. Okay, so an example might be something like y is equal to c over x. Okay, that is our our solution. Okay, now, excuse me, c up there is a constant. Okay, so it could be any number we want. Okay, let's take a look at how this works though. Okay, so we've got our solution equation. Okay, and we'll graph it for various values of c. So we'll start off with an easy one first. Okay, if that was a 1, what's the graph of 1 over x typically look like?
When x plus
Not you're thinking integral. Yes, exactly as Jack. It does this number. Okay,
Yeah.
curves like that there. Curves like that there. So this is when c is equal to 1. Okay. When c is equal to 2, what happens? This thing gets a little shallower. Okay. It does that number instead. And when c is equal to 3, it's even more shallow. Okay? Okay. Whoops. Where'd c equals 3? We got that. When c is a fraction, though, it gets more extreme. It almost forms like a right angle diagram. So it might be like c is equal to 1/2, something like that. Okay? What happens when c is negative?
it flips.
It just
I don't have
flips.
colors, Mr. Dowell. I can't write this.
Well,
The pen, you have a pencil in your pocket?
okay.
Mr. Dowell.
By pressing down paper.
Yeah, Mr. Dowell, aren't you colorblind? How can you even see the difference between those?
I'm really baffled.
I got buttons down here that lets me
There are
do
many variations.
different
Wait,
ones.
no, I'm not.
There's no yellow
Look
one
at-
right
look
now.
at
There's
the yellow button.
Oh, the yellow one's easy. It's the one I drew last. I can see yellow.
No, like, how'd you get
The
it?
blue one is on the as the innermost curve.
Which, are you red green?
I'm thinking the red and green. I want to say, I think this curve here is the red one. I think that was the green.
Oh!
You're wrong.
But
You're right, you're right.
Yeah.
Right, these are tissues.
How did you
He's
do
right.
that?
Y'all don't mess with him.
How do you know that?
How do I know that? I know that because the buttons themselves. I know the red one is closer to the black one. I just did the buttons in the order that they came in. Okay, so that's really why I was able to remember that. Be honest with you though, I cannot actually see the red or the green one as red or green. I just see them as bad.
Does it say red, though?
Bless you.
That's not.
Huh?
Does it say the word red on there, though?
No, it's just been I've been using this for over a year, and after a while you figure things out.
Huh.
Yeah.
Mr.
Um,
Dowell is it?
If I was
He's a wizard at it.
if I had never used the smartboard before and you asked me that question, I would have a much harder time answering you.
Yeah.
Although I would still probably, the way they tint the two buttons here, I would probably say that the red was indeed red. Anyway, the green one, I had no idea if it's green or not.
What color is this book?
Okay.
There's no way.
Oh!
It
I
can't
don't know.
Can I say that?
Some color.
What does
Where's
it
that?
look like to you? Gray?
Look. I don't know. Gray? Yeah,
What's the-
kind of, but
what's
not
the
in the
circle
not in
part
the
in
usual
the-
way.
in
All
the-
right, we gotta get back to this. We gotta do. We gotta ask me these questions are after class. We gotta do slope fields. Okay.
I wonder what
Alright.
orange looks like to you.
Anyway, but this is how you do this is what's called the solution curves, okay? Because you're graphing out the solutions, but you're graphing out various ones, okay? Again, somebody when I ask me, well, how many do I graph out? When do I know to stop? The conditions of whatever problem or conditions of whatever we want will tell you how many of these we actually do, okay? This is just an example, all
Hey,
right?
Mr. Dell,
Yeah.
they've stolen all my stuff. He says my pen.
Okay, could you return him his stuff so you can take notes?
I've gotten his pen.
Because people passed it down. I'm not an idiot. Let's go. Okay. Slope fields. All right. The next.
Hey, just trying to learn, man. You take that away from me.
Okay. The next type of graph you'll see with differential equations is something called a slope field. Okay. A slope field is a graph of y prime equals f of x, y, okay? What you're doing here is you're actually graphing what the slope does at any specific point on the xy plane, okay? Graphing, it's a graph of the slope at any particular point. So, this is not going to be a graph of like a full curve or sketch. In fact, instead, this is going to be just a representation of what the slope would look like for any given point. So, for example, if I had a differential equation such as y prime equals x minus y, the graph of this is essentially just going to be what the slope is doing at various locations. So we'll keep a small one, like so. So basically, the graph of this might be something like, okay, when both x and y are 0, what's y prime going to be? Nothing. It's also going to be 0, right? What's the slope of 0 look like? Flat line, right? So
I don't like this all. We're getting back to the stuff that I hate.
we have something like that there. When x is 1, but y is 0, what do we get?
1.
1. We have a slope of 1. Slope of 1 looks something like that there.
Jesus.
Okay? When x is 2 and y is 0, we have a slope of 2. Slope of 2 is a little bit more extreme. When x is negative 1 and y is 0, negative,
I don't like it.
more extreme.
Scarter, how you feeling?
It's too extreme.
That one was.
Okay? And so you're going through, and this is exactly what you're doing here.
Wait,
Okay?
negative 1 is definitely more extreme than negative 2, right?
No.
No, it's not.
Negative 2 is going down like that, negative 1 is going down like that. Okay?
No, I
We
was
can come
thinking
through here,
relative to the
okay,
black line.
and do this for any point. So, for example, when x and y are both 1, it's horizontal again. Okay? When they're both negative 1, it's horizontal. And in fact, they're always horizontal there. If x is bigger than y, the thing has positive slope. So, positive, a little bit more extreme, really extreme. Okay? Not so bad there, more extreme, very extreme, super extreme. And now I stink at drawing, so I'm not going to be able to get this perfect. But when y is bigger than x, our graph is going to be negative. Okay? More extreme, very extreme, super extreme,
This is a
very
thing?
extreme. Yeah.
Jesus.
Okay? And one more point there. There we go. Okay. And so what we've done there is we filled out, and we went through and just filled out when x is 1, y is 1, when x is 2, and y is 1, when x is 3, and y is 1, etc. We can go through and fill out a picture of this. And this is telling us what the slope would be doing for this differential equation at any specific point. Also notice, too, how I don't have a specific equation given. Okay? This is a general case. Okay? So it's kind of saying, what's this thing going to do for any point I choose? You can actually take this a step further and start connecting the dots and see what sort of picture you get. If I started at, let's say at 0, 0, if I followed what the slope said, it's horizontal, so it would come through, connect to the next point, come up like that, do the same thing over on that side. What type of picture do I get? A parabola. So, and in fact, if you connect the dots anywhere along here, guess what type of picture you get? You end up getting a parabola.
That's
Okay.
a mess.
Wait, what dots are you?
Or the little slope lines.
I feel like that's not.
Oh, I
You
see.
just follow what they say. Like, for example, this one says
that's cool.
you go down, you have a slope of negative 1. Well, if I have a slope of negative 1, the next point I hit has a positive slope of 1.
a weird.
So it would be
Just be aware.
also a parabola.
Just be aware.
Okay? Just starting at a different
Wear
location.
like a red, green t-shirt.
Okay? And so you could go through and see it. There's a really good picture of this on page, I want to say it's like,
Wait, put it on the flat screen?
no, take too long to do. On page 409 in your book, there's an excellent picture of this being done. Okay? But essentially, you can go through at any of these locations, and you would get a parabola if drawing this way. So, I can surmise that whatever the general solution of this thing is, it's going to be parabolic. Okay, it's going to make a parabola. And in fact, if you actually were to find the general solution, you do get a parabola. Okay? So it's pretty impressive that way. Okay? Any questions? All right. So this is how. This is what we're going to be up to for the next couple of days. Okay. So if you have any questions, let me know. You'll have some homework posted on Canvas tonight.
Not this 3.